Welcome back to AP Calculus. This unit is the definite integral unit, and we're starting our first lesson with estimating with finite sums. So a lot with integrals, we're just actually calculating the area underneath each curve. So we're going to introduce that, starting with this first example. We've been given various lines here, and we want to find the area underneath this. So the easiest way to find the area underneath the curve for this one is to section it out so that we have either squares or rectangles, because it's easy for us to calculate the area of a square and a rectangle. You know the area of a rectangle is length times width. So I'm going to go ahead and separate these into 4 rectangles. Now we're going to calculate the area of each by multiplying its length and height. So our length down here, or width down here, is 2. And our height is 2. So this area then is 2 times 2, which is 4. Then our next triangle, or rectangle, is 2 times 3, which is 6. Then we have 2 times 1, which is 2. And the last rectangle is 2 times 5, and that's 10. Then we're going to add up each area, and altogether the area underneath that curve is going to be 22. Now try the next one, do the same sort of thing. You want to separate each section into a rectangle or a square, and then you're going to find the area of each and then add them together. So go ahead and do that and press pause. Okay, so for this one, we're going to section it out into 4 sections, as so. The first one, we have 1 times 5, which is 5. That's 3 times 2, which is 6. 1 times 3 is 3. And then 1, 2, 3. 3 times 4, it's 12. And then you're going to add them together, which is 26. So then your area underneath this curve is 26. Now we're going to try slightly more difficult ones. Our functions don't tend to look like these, where we just get a bunch of straight lines. Usually functions are curved. So we're going to try to approximate the function given to us. There's several methods in doing this. Later on we're going to learn 3. But for this first one, the idea is I'm just going to underestimate and try to keep all my rectangles underneath the curve. So this will be an underestimation. So from the first one, from this point, I'm going to use that to help me guide to my first rectangle. And then from the second point, I'm going to use that as a guide again to create my second rectangle, and then so on and so forth. Okay, so I have 4 rectangles, and I can calculate the area of each just like in the previous 2 examples. So that's 2 times 2, which is 4. 2 times 3 is 6. 2 times 1 is 2. And 2 times 5 is 10. So again, if you add this up, that's 22 for our area. And this will be an underestimate for f of x. Now I can try a different approach for this one, just to try it out. Let's try to make our rectangles, and we're going to use the most left point to help us determine the height. So this is the most left point. That means I'm going to create a height here. And that will give me my first rectangle. I had a second point here, so I'm going to use this point as my height and connect it with the next one. Then again, I'm going to use this as my height, this left point. And then I'll use this one up here as my left point, and then that's it. So we have 4 rectangles, and then we're going to calculate the area of each. So this will be 5. This is 1, 2, 3 times 2, which is 6. That's 1 times 2. And this is 1, 2, 3 times 4, which is 12. So again, if you add this all together, it's going to be 25. So we're going to do this formally now, and this is called the RAM method, or in other words, Riemann sums. So there are three that we're going to consider. The LRAM, which is using your left endpoint for each subinterval. That's what we did here in this example. Then you have your right midpoint to create each subinterval. That's called RRAM. And the last one is you're going to use the middle, the midpoint of each subinterval, and that's called MRAM. So let's look at actual examples of this. So in this first one, if we take a look at all the left points, this one lines up with a line that was created to create the rectangle. And here, this point was used to create the height of this rectangle, and so on and so forth. So this looks like this is the left-hand Riemann sum. In other words, that's your LRAM, left-hand Riemann sum. Okay, now let's look at the other one. Now, this one looks like it's not either of these points, because if I was going to create it from my left hand, it'd actually start over here. But that's not the case, so it's not the left-hand Riemann sum. And if you looked at the right-hand Riemann sum, it's not this one either, because then I would have to create a rectangle that looks like that, because that would be my height. And again, that's not the case. So this must be the midpoint one, the MRAM, because I picked a middle point in between these 2 points to create the height of my rectangle. So this is the MRAM. So for example 2, the total area under the curve then is approximately equal to the total area of all the rectangles. Which of the graphs above give a better approximation of the area underneath the curve? Why, and then how can it be improved? Well, if you look at LRAM, it looks like we are underestimating a lot because we're missing sections such as these. But then again, we do have this section over here that could make up for some of that. In our MRAM, overall looks fairly consistent. For every empty piece, we do have a bit more to cover it up. So overall, MRAM is fairly consistent, but LRAM can be fairly inconsistent. Usually with the left-hand Riemann sum, it is an underestimation. Your MRAM is kind of in the middle between the left hand and then the right hand. So your right hand Riemann sum, your RRAM, would most likely be an overestimation. So to answer example 2, it is going to be the right graph, your MRAM graph, because we have less gaps and overlaps. The right graph, which is your MRAM, that's because we have less gaps and overlaps. So in summary, the first step to do something like this is to divide or partition the interval into subintervals. So for example, these ones have 4 subintervals here because we have 4 rectangles. Then we want to create n of those rectangles whose basis is equal to the width of the subinterval and whose height is determined by the function value at the left point, the right point, or the midpoint. And then we want to find the area of all and then add them together. So we're going to do RRAM for this one as an example, and then we're going to do MRAM for this one, or LRAM, sorry. So for this first one, if I'm doing RRAM, I'm going to look at the right-hand point. So these two are the set of the points, and I'm going to look at the right one. So this is where I'm going to create my rectangle. I'm going to use the second point to determine my height. Then we'll do it again here. This is the height coming from this point. Then the height coming from this point. The height coming from this point. And then lastly, the height coming from this point. And then we're going to find the area of each rectangle and then add them together. So this will be 2 times 3, which is 6, 2 times 3, which is 6, 1 times 1, which is 1, and then we have 1 times 5, which is 5, and lastly 2 times 5, which is 10. So we're going to add these all up. That means that we have 28 for the RRAM calculation. So the next one we're going to use our left-hand Riemann sum. This means I'm going to use the most left point to create the height of my rectangle. So I'm going to use this one. This is going to create the height at the same place. So that's my first one. Then between these 2 points, this is my most left point here. Again, between these 2 points, this is my most left point, so that's my height. Then my most left point between here and up there is this one. Then my most left point between here and here is this one, so that's that height. So we have 1, 2, 3, 4, 5 subintervals. Again, we're going to find the area for each rectangle. So this is 2 times 2, which is 4. Again, 2 times 3, which is 6. 1 times 3, which is 3. 1 times 1 is 1. And then 2 times 5 is 10. So we're going to add these again all up from the 5 subintervals, and this will be 24. So as you can see, our RRAM is an overestimation, our LRAM is an underestimation. And if you would calculate the MRAM, you're going to get something kind of in between. So here's the next example. We're going to do LRAM, RRAM, and MRAM for this. And we're going to do it from x equals 1 to x equals 3. So for our LRAM, we're going to use our most left point, and it says also use 4 rectangles. So the other points I'm going to consider are the ones in here. Kind of the middle of all these, of the 2 points. So like at 1.5, 2, and 2.5, and so on. Okay, so for our first one, since we're doing the left-hand Riemann sum, in between these 2 points, this is my most left point, so I'm going to create a rectangle here. And then from these 2 points, this one's my most left point, so I'm going to create a rectangle here. Then this is my next one, because this is my most left point. And then this is my most left point. And those are 4 subintervals. And then now we're going to do the calculation for it. So each of these is worth 0.5 down here. If you look at our width, it's 0.5. And we're going to multiply by the height. So the first one is 1. Then we have 0.5 times what looks like 1.25. Again, our width is 0.5, and our height now is at 2. 0.5. The next one looks like it's at 3.25. Okay, so we're going to multiply this all together and add them up. So it's 3.75. What you could also have done, because we know that all these widths are the same, you could also have done 0.5 times 1 plus 1.25 plus 2 plus 3.25, and that would give you the same sort of thing. Okay, so now let's do our RRAM, and I'm going to draw in those same points found on this graph. Okay, but now we're going to look at our most right point. So between these 2 points, this is my right point. So my height is going to be based off of this, the most right point. Same thing over here. Okay, so That's going to be our 4 subintervals there and our 4 rectangles. Again, if you take a look at the width, they each have 0.5. And then now we're going to look at the height of each. So we have 1.25, 2, 3.25, and lastly 5. I'm going to do this calculation. That's 5.75. And lastly, the MRAM. So the MRAM is going to be the midpoint in between the 2 points, but I'm going to again write down the points of each and just draw that in there. Okay, so my midpoint in between these two is going to be this one here. Then my next midpoint looks like it'll be about there. Then my midpoint between these 2 points looks like it's going to be about here. And then lastly, the midpoint between these two looks like it's going to be about here. And now in order to get these points, we do need to plug it back into our function to find it. But our width is the same. So to find what this would be, you're going to need to plug into your calculator. I'll just do the first example for you. The midpoint's coming from 1.25, x equals 1.25. Because that's in between 1 and 1.5. Now we just need to plug it into our function. So y is equal to 1.25 squared minus 2 times 1.25 plus 2. And if you do that calculation, you are going to get 1.0625. So that's the height of our first one. And then for the second one, you're going to plug in 1.75 to find our height. And then again, you would do 2.25 and 2.75 for your x values to find your y value. So you're still going to follow that same sort of thing, just plug it back into y equals x squared minus 2x plus 2 to find these values, but I'm just going to go ahead and give them to you. So these are the heights for each of those triangles. And then your final calculation will give you 4.625. So if you take a look at the LRAM, the RRAM, and the MRAM, your MRAM's right in between your LRAM, your RRAM. So this is going to be the most accurate you can get out of all 3 different methods. Okay, in this next example, we're given a table of values. And it's given us velocity of a train moving on a track over 10 seconds. So we don't always need to have a graph to estimate the area. We can also just read off of a table of values to do the same thing. So we're going to do an LRAM and an MRAM calculation, and we need 10 subintervals. And we're going to estimate the distance traveled by the engine in the first 10 seconds. So again, remember your LRAM, you're going to use the most left point. And if you take a look at the width, because usually it'll be v over t, we're going to use time to determine our intervals. So if you look at time, it looks like our width for each of these is going to be of 1. It doesn't jump at all. So your width is going to be 1. Remember, in this case, it was 0.5 in the previous question. In this case, it's going to be 1 because you can tell it's kind of like our x value, and the velocity will be our y value, which is the height. So we know the subinterval will be a distance of 1 each time along the x-axis. So that is going to be our length of 1. And then we're going to multiply it by the height, which is found in the velocity part, your y. And we're going to take the leftmost right height out of the intervals. So between 0 and 1, I'm going to take 0 because that's my most left point. Then between 1 and 2, I'm going to take 12, because that's my most left point, and then so on. So the next between 2 and 3 will be 22. Between 3 and 4 is going to be 10. Between 4 and 5 is going to be 5 as my most left. Between 5 and 6 will be 13 as my most left. Between 6 and 7 is going to be 11. Between 7 and 8 is going to be 6. Between 8 and 9 is going to be 2. And then between 9 to 10, that's going to be 6. So we're just going to add these all together and then just multiply by 1, which is 87. And if you think about our units here, it's going to be in centimeters because we're looking at distance, and our velocity is centimeters per second. Then for our MRAM, we're going to do something very similar, but in this case, we're going to do 5 subintervals, which means that I'm going to look at 0 to 2, and then 2 to 4, 4 to 6, 6 to 8, and then 8 to 10. And that will give us 5 subintervals. And we're going to take the middle value of each. So our subinterval, again, if I'm going from 0 to 2, that's a distance of 2 for our width of the rectangle. And if you look at 2 to 4, again, that is another 2. From 4 to 6, that's 2. 6 to 8, that's 2, and so on. So our width for each subinterval is 2. Now we're going to find the height. So our first interval is between 0 to 2, and that middle number is going to be 12. And then our next one's from 2 to 4. And the middle one, middle velocity, is going to be 10 in between 2 to 4. And then we're going to look at 4 to 6. That middle number is going to be 13. Then 6 to 8, that middle number is going to be 6. Then 8 to 10, our middle number is going to be 6 again. Then we're going to add these all up and then multiply it by 2. So that it's going to be 2 times 47, which is 94 centimeters. The last rule we're going to go through is the trapezoid rule. So rectangles are a fairly good approximation, but as you can see, once we have a curve like this parabola, it's probably better to create trapezoids instead. So the area of the trapezoid is 1/2 times the height multiplied by b1 plus b2. So your height is along the side here. b1 is one of the lengths, and then b2 is the other. So we're going to apply this for our next example. And we're going to create 4 trapezoids here from 1 to 3. So again, because we're creating 4 trapezoids, we're going to use 1.5 and 2.5 to help us create this as well for those x values. So our first trapezoid, we're just going to kind of follow the length of the curve, as so. Then we're going to go from 1.5 to 2 and create another trapezoid there. Then 2.5, connect it to create the trapezoid, and lastly, our last trapezoid, connect from these 2 points and a straight line like that. So we have 1, 2, 3, 4 trapezoids, and now we're going to begin by finding the area of each trapezoid. So again, our formula is 1/2. Let's write this on the side first. Okay, so if we look at this first trapezoid over here, we need to find the height, and the height is going to be 0.5 in this case, so that's kind of the bottom part along the x-axis, that's our h. And then B1 is one of this length, one side of the length, and then the other side. So we have 1 for the left side of the height, and then the right side of the height, that's going to be 1.25. Okay, so that's for one of them. Now the next one, again, we have a width of a half, or in this case, your height, because we're talking about trapezoids. And then we'll do one length plus the other. So we have 1.25 plus 2. Remember, your 1.25 is the left side of that trapezoid. The right side of the trapezoid has a length of 2. Then the next one, a length of 2. And then the other length on the right side is 3.25. One more trapezoid to consider. The left side is 3.25. The right side is 5. Okay, so we're going to calculate each of those and add them up, which is 4.75. So notice we have the same subinterval each time. To actually simplify our work, we could have just had the 0.5 at the very front with a half, and then have our lengths all in brackets within another bracket. So for example, you'd have 1 plus 1.25 plus 1.25 plus 2 plus 2.3.25 plus 3.25 plus 5. So basically you can just factor out the half and the 0.5 out, and then just focus each on the B1 plus B2 and you would get the same answer. So please check your homework and practice on the LRAM, MRAM, and RRAM and the trapezoidal method.